Hello guys, hello world, hello Philippines. Welcome to my YT channel. Okay, so I'm going to discuss to you about the first law of thermodynamics and of course a little bit of second law of thermodynamics, but more on the first law of thermodynamics. Okay, so in thermodynamics problem, don't forget to memorize the heat engine principle. Okay, so this is all about isothermal thermodynamic process. Okay, when we say isothermal, there's no change in temperature, so letting the temperature is constant, but the change in internal energy is equal to zero, meaning to say heat is equals to work. Now, in thermodynamics, there are two key terms. We have the system and we have the surrounding. Okay, so the surrounding is the equivalent part for that. Another term for that is an environment. Okay, so let's do first the heat. So meaning to say the thermal energy. So if the problem will say the heat is added to the system, okay, heat is absorbed to the system, so that is a passive heat. Okay, for example, our system is specifically the heat engine or the car engine, something like that, because heat engine is an example of the change in internal energy is equals to zero, or isothermal, right? Okay, so that is heat energy is being transferred, so that is passive heat. So the negative heat will be the heat released to the surroundings, or the heat released to the environment, or the heat given off to the environment, or the heat given off to the surrounding, or the heat occurs to the environment, the heat occurs to the surrounding, or the heat transferred to the surrounding, the heat transferred to the environment. So that is a negative heat because we are referring to the system. Okay, if that is transferring the heat energy to the surrounding, to the environment, meaning to say we have a negative heat because it loses heat from the system. Okay, if the heat occurs to the environment, if the heat occurs to the surrounding, if the heat is released to the surrounding or given off to the surrounding, so it is a negative heat because it was being transferred or transported or released to the environment or the surroundings. So our system, which is the heat engine, heat will be negative, something like that. So that's a negative heat because our reference is always the system here in thermodynamics. Okay, so now our example is a heat engine. So automatically we have different formulas for this, right? So since this is a heat engine, so there are problems that relates to the efficiency of the heat engine. So usually it should be, not usually, technically it should be work output divided by work input times 100. Since there's no change in internal energy is equal to zero, then heat is equals to W. So we will say also that the work task of the system, which is the heat engine, or simply the W, okay, is equals to the work output automatically or technically divided by the work input. And our work input, of course, that is the heat absorbed in the engine, or the heat absorbed through that system, which is the heat engine. Okay, so from the source, the heat from the source. So that is the passive heat because that is the heat from the source and the heat is being absorbed there like that. So that is our passive heat in the denominator. Okay, now our negative heat is the heat that occurs and transferred to the surrounding, which is the cyclic process, in a cyclic process in the environment. So this is applicable to Carnot cycle. Carnot cycle meaning CARNOT cycle. So this is all about heat engine, okay? Something like that. So our formula will be efficiency is equals to W over QC. Okay, QC is meaning heat absorbed to the system or the heat engine. Okay, so we can say also, I have to write, so you cannot memorize, right? So if you are giving, if the problem give you two systems, heat engine 1, heat engine 2, if the problem will give you heat engine 1, heat engine 2, then you can correlate the first system to the second system, and then using the same formula, Q is equal to W, something like that. So in heat engine type of problem, heat engine, okay, so delta U is equal to Q minus W, change in internal energy is equal to 0, therefore Q is equal to W. This one. This is a heat engine example for the first law of thermodynamics. I think so. Yes, because the second law, it involves about the change in Gibbs free energy, and then is equals to the internal energy minus the enthalpy of the system. But this is not second law. I think so. Second law or first law? I think first law of thermodynamics. Okay. So there's also Gibbs free energy is equals to delta U minus enthalpy, right? Like this. Okay, this is for the second law, right? Change in Gibbs free energy is equals to change in internal energy minus the enthalpy. So this is the heat, total heat content or the heat transferred, something like, or just Q, okay? So since we have entropy is equals to the heat enthalpy over T or Q over T. Enthalpy H is just equals to the heat Q. So which you will use? You will analyze just the problem. So delta S is equals to H over T, then therefore we can say delta Gibbs free energy is equals to delta U minus delta S times T. And this is the second law of thermodynamics, and this is the first law. Right? So this is our second law of thermodynamics. Delta U is equals to, delta U, change in Gibbs free energy is equals to delta U minus, okay, delta change in entropy times the temperature. Okay, now going back to the heat engine, so we can have efficiency is equals to work over Q absorbed for the heat by the heat engine times 100%. This one. Efficiency, work output, okay, or work task by the heat engine over the work absorbed by the heat engine times 100%. Sorry. And then we have work is equals to, okay, QC minus Q, let's see, E. Okay. QC meaning heat absorbed, okay, so work is equals to heat absorbed QC minus the heat released to the surrounding. The heat released to the surrounding, or the heat transferred to the surrounding, or the heat occurs to the surrounding, or the surrounding environment is just the same. Like that. Released, this is absorbed, this is like that. Okay, this is referring to the heat engine, this QC. Okay, this is referring to environment surrounding, this QH. Okay, substitute within a formula. So we can say efficiency is equals to QC minus QE over QC. So therefore 1 minus QA. So this is our formula. Efficiency is equals to 1 minus QA. Heat released to the environment. Okay? Like this is our formula for efficiency. Okay. Then therefore we can also say that the mass and specificity is constant all throughout the process in the equation Q is equals to mc p dt, or in the process of delta H is equals to entropy times temperature, and treating the temperature is constant, right? Like that. So we can say also that in terms of temperature, if we try to solve for temperatures, so we can have efficiency Tc minus Te over Tc is equals to 1 minus Te. So it's also like this. Tc minus Te is equals to over Tc, or 1 minus Te. Te is the temperature transferred to the environment, or the temperature of the environment. Okay. And then Tc is the temperature of the heat engine, or the temperature absorbed to the heat engine, like that. The word C and E, it depends on you. If you put S on E, if you put A absorbed in C, it depends on you. It's just only a representation. Okay, like that. So through this equation, if there is heat engine problems, then we can solve for the work, the efficiency, like that, and the heat transferred to the surrounding, and the heat transferred to the system, or heat absorbed to the system, something like that. Okay, so it's gonna be easy for explanation, but when the problem comes, you have to analyze very well. Thank you so much for watching this live video, and you can comment in the comment section down below, and you can click the notification bell for some newest updates of I'm a Senior Eternal Voice. And then if you are not subscribing yet my channel, then you can subscribe now. Thank you so much. Bye bye everybody. God bless.